So hello everybody, welcome back to another video. This time we will go into solving the classification problem that we have seen in the last lecture, basically practically. This is also a follow-up onto the other courses that you have seen so far, so on the introduction to Python, on the data cleaning section, and right now basically we will go into how to use, how to train a classifier using the scikit-learn library. This will be kind of the topic of the day. So in order to do this, we need basically the clean data set that we have from the Python data cleaning session. The clean data set, you find it in the URL outlined below here. We don't need this anymore. You can pause the video here, copy paste this. It will probably also be in the description of the video. I will close this here right now. And then we start with our new Python notebook. So here we see my Python notebook environment. I have downloaded this file here. I started the Python notebook environment in the same folder as where I have downloaded the file. If you use Kaggle or Google Colab or any other type of online notebook, you probably have to upload this file. It's very easy. You just look at the documentation of the respective system, how to upload files. Here we have this file locally on the disk. We have our Python notebook environment, and I will open a new Python notebook so that we basically can get started with our session with a blank notebook right away. Okay, we select the Python 3 kernel and we have our new notebook up and running. And what do I want to do? Basically, I want, of course, to open the file that we have downloaded, so our cleaned data set that we have cleaned basically in one of the prior sessions. And investigate it a bit and start training classifiers on it. So let's get going. What do I need to do in order to import the CSV file? Well, we can use, as shown in prior sessions, the pandas library, as you all know right now. I will do this import pandas spd, and we have our pandas library loaded into memory. So let's get started. I will call this data frame X for convenience reasons. So we can use the read CSV function as we have seen in prior courses already. And we open our file that we have called train data cleaned in this case. If you have it somewhere else, of course, you have to open the appropriate path. That's the way it is. Okay, and if I type X right now, I have my data frame in front of me, and we see in this data frame that this is the clean data frame that we had, but due to the export import, basically we have this extra column here, this unnamed 0 column, and we want to get rid of it. How do we get rid of it? We already know about the pop functionality that we have here. And you just say pop, and this column is called, let us recap it, unnamed 0, so we have it here, unnamed 0, and we have removed it from our data frame, and have right now a clean data frame, yeah? So let's get a bit over this data set, what is going on here. So as a bit discussed during the different sections, we have basically here features. So we have radius, texture, perimeter, 0. Then we have this thing here 3 times. So we have 0, 1, and 2. And beside this radii and textures and perimeters, we have an age of each of basically patients, and we have a cancer type, which basically says if this person has cancer or not. Yeah, and the question is, what we want to do is basically take all these features, so including the difference in diagnosis and treatment data that we have calculated in a prior session, So we take all these features and want to build a classifier which tells us, okay, is this a cancer type, or is this cancer, or isn't this cancer? Okay, from the features that a doctor basically has put into this data set. Okay. And this is what we want to train. So if then we get basically a new patient and we get these new features from this new patient, we can then automatically predict if this patient has cancer or not without having a human decision or helping in a human final decision to be made. Okay, this is kind of the goal of this session and how we will do this. So we see basically right now we have our features, but within our features we have also our labels. And the first thing that we will do is we will separate the features from the labels. The label is the cancer type. How can we do this? We can use this pop functionality as I've shown you just above in order to just pop this out of this table and put it into a new variable or data frame, in this case, which has a single column, which is just the cancer type column. Okay, so we will take this cancer type here, we will copy paste this here as a string, of course, like this, and we popped it out. If you look at Y right now, we have our labels stored in Y, our features in X. We're good to go to train them all. No? So in the scikit-learn, basically references, X are always the features, Y are always the targets or labels. This is also in most of the machine learning literature named like this. Okay, so fine, so good. We come to our basically to our data set, and going back to our data set, let's look a bit into it. We remember we have this columns functionality just to make sure which columns we have right now. So these are all our columns. This is the X. If you do this on the Y, we see we have no columns because we have just one single column. Okay, fine, so good. So this is basically the single Y column. We have here in X, we have basically these columns, and these are the labels to our Y column. So this here are the labels, these here are the features, the different features that we have. Okay, so fine, so good. Right now, when I look at these features, what we find basically is, and what we want to avoid is that all these columns, especially when we look here towards the end, we have the age, we have the parameter, we have the texture, we have this difference in diagnosed treatment date, and we see that all of these columns are of different magnitudes. Okay, so these here are in millions, these here are in hundreds, these here are maybe in below 100s, and we have to get them all into the same magnitudes, because otherwise our machine learning algorithm might not work. We want all dimensions basically of all features, all feature columns kind of in the same magnitudes. So how can we do this? In order to do this, basically the scikit-learn library gives us something which is called the standard scaler. What does the standard scaler do? It takes each of these columns and it kind of brings them to a mean of 0 and to a standard deviation of 1, and rescales the values accordingly. And this is exactly what we want, because then we have values that are kind of everywhere in the same magnitude. Okay, so fine, so good. Let's try this out. Let's use the standard scaler. This is a typical pre-processing step. So if you remember basically one of the first courses where we talked about pre-processing, so one of the pre-processing steps that we do here, and this is also why this is in scikit-learn, in this pre-processing subsection where we find the standard scaler. Okay, so rescaling the dataset. Okay, I have the standard scalar imported, and right now how do I apply this how do I scale my data set, how do I do this, perform this transformation. So first of all, I have to fit the standard scalar, so we create the standard scalar like this. We call it the scalar, so we create our scalar and we use the standard scalar methodology here, and we use basically the fit method of the standard scalar. So basically what happens here is it trains the scalar according to the dataset. Why do I name this like this? Because then I can transform, of course, the dataset, but I can also transform new data that might come into my dataset. So I can store kind of the transformation that it will make on this dataset for future use, so that I can use it in order to predict new data that comes into my dataset. Okay? Because otherwise, of course, I could never get to a mean and standard deviation of 1, which of course with future data might not be the case, but I want to keep this transform that I use during that I have applied here on my dataset for future use if new data arrives, for instance. Okay, so I store this in the scalar type, and then I use the scalar to actually perform the transformation on the dataset that I have trained it on here on this X feature vectors. Okay, feature matrix. Okay, let's do this. I will call then my new features the scale features with this underscore s, and I use the scalar and I transform it and apply x to x's. Okay, and I have my scaled data. Basically, if I show it right now, it's a NumPy array. So this matrix that we have here basically has been at the same time transformed into a NumPy array, and we see that all the values kind of are in the same range. And when we then perform, basically, when we look at what is the mean of the story here, as this is a NumPy array, we see that the mean is 0, and if we then look at the standard deviation, we see that the standard deviation is 1. Okay, this is what we want. Right now we can basically train our first classifier. Yeah, in order to naively train a classifier without doing a training test set split, which of course you don't want to do, we will show it anyways, so that you kind of get a hands on how these classifiers work, how these classifiers run. So we use the support vector machine in order to classify, to train a classifier. We have seen the support vector machine in one of the prior lessons. Let's quickly look into it, what this looks like. So we take, of course, as I said, the scikit-learn library. In this scikit-learn library, you have a support vector machine module, which has this kind of support vector classifier functionality. Okay. So we import this here. So this is a typical classifier. You could import other classifiers. We will show them later on during this session. It's not so important. Just to get started with this one. So in the scikit-learn nomenclature, basically what you do, we take this support vector classifier and we define some hyperparameters. So we use the kernel. As I said, there is the kernel trick. We have talked about this in the last lecture, which basically allows you to use this support vector classifier in a curved space, and to get probably better predictions. In this case, we don't want to do this. We just want to use the linear classifier that we have seen, which uses the Euclidean space basically to classify without making any kernel trick. So this is the classifier. How do I train the classifier? This is for all classifiers the same procedure. So you take the classifier, you call the fit function, and we use our scale dataset, and we use basically our y, as this is still kind of a pandas data frame. we will use this toNumPy functionality of pandas in order to have NumPy array and NumPy array here, and don't run into further trouble. Basically, this also should work if both are pandas data frames. The scikit-learn framework is intelligent enough in order to treat this data. Here we have NumPy arrays, just to keep it at the same, I will call here this toNumPy functionality. Okay? Okay, so far so good. We train this here. We fit our classifier, and we see we have our support vector classifier fit. And then if we want to do a prediction, you have basically the predict functionality. And here you can basically insert one row of our X dataset. So if I take here basically, for instance, we can do this like this, XS, this should basically work like this. If I take here XS0, I should get a prediction out of it. So just note that I needed to have this here embarked into a list, so basically I could have multiple values in the list and get then multiple values then out for each prediction. So here I get basically that XS0 is not a cancer. We could basically verify this right now with the Y. I'm not sure if this works right. Anyway, this is bogus because we have no test set training set split, of course, in order to validate this. We trained on the whole data, which is something that you never should do. So you should have a test set training set split or cross validation, as we will see in the further of this course. Okay, so far so good. We have our prediction. Right now we go into the cross validation and finding basically the best classifier. So how you do this in reality, how you do really train a classifier that you can trust on. Okay. So in order to start with this, we need several functionality from the scikit-learn, basically from the scikit-learn library, and we will perform model selections. We will not just use one classifier as here, but we will build a model zoo, as we talked about it in the lecture, and find from the model zoo which one is the best model in order to perform this cancer or not cancer prediction from these features that we have up here. And from this, from all these features that we have basically in our data set. Okay. So how will we do this? We will use from our scikit-learn model selection. We go here, import, and we import cross score. So we need a score, of course. So cross validation scoring. We need something which is called the shuffle split in order to create our cross validation splits. And we also need a train test set split later on in order to perform the final, basically the final model training. So train test set split. Test split, this is called in here, and we evaluate this, and I have a little spelling mistake here, and we have basically what we want. We have this kind of model selection functionality that we need for our further evaluation. So the next thing that we do is we build what we call here the cross validation, so CV. And how do we build this? We use what we call the shuffle split. And we use the shuffle split, so basically we want to have n splits. So we want to have 10 splits, and the test size, let's make it always 0.5. So what happens here? So as I told you the last time about the cross validation, here I perform 10 splits. So randomly, basically, it selects half of the data. It puts this half of the data into a test set, okay? and we have a training set, a test set, and we want to use basically the training set in order to predict on this test set. Okay, that's basically it. That's basically what happens here. Okay, easy as that. This will be our cross-validation. Okay, so we train on half of the data set, we test on half of the data set. This is basically how it works here. Okay. Next step, I will just to make this sure here. There is also a train size. Let's make sure, as far as I remember, let's make sure that this is also 0.5. Okay. Okay, so we have our shuffle split, train size, test size, 0.5, 0.5. This is how it works. Half of the data set is the training set, half of the data set is the test set. The test set is randomly chosen. That's how it will work. And we basically choose 10 times randomly half of the data set, so that we have 10 different splits in order to perform cross-validation. Okay? So fine, so good. We then want to evaluate our scores, and we can then use basically a classifier in order to evaluate the scores. But we don't want to use one classifier. As I said, we want to use multiple classifiers in order to do this. Okay, so for the quick purpose how to do this, we will just show this with one classifier, so with this support vector machine that we have above here. And we have here a cross-val score. Okay, so cross-validation score, we use the classifier, which is the support vector classifier that we have from above. We type in our training set, our features basically, our labels, and it automatically will split this according to the cross-validation by calling CV equal CV. Okay, and when I run this, it will run basically all the splits with this classifier very quickly. And then if I look at my scores, what do we have? We have scores set up pretty well basically, as we can see, and this is then basically the result of our trained classifier. So we could train a classifier with this, with a training set split like this, and obtain scores like this, with just using the linear support vector machine in order to perform our classification. And we see that we, in all the cases at least, we are better than 0.8. So in 80% of the cases we make the right prediction, which can help, for instance, not of course in medicine to make the final decision, but in order to make a decision if this guy has cancer or not. Okay, so far so good. In this case the machine would say, I don't know, under this confidence interval the guy has cancer or not, according to our prediction score. Okay. Okay, so far so good. That's all nice. Right now we want to build our model zoo and see if this was the best, basically if the classifier that we have fitted, that we have built here, the support vector classifier that we have evaluated with our cross-validation here, is the best. Of course, this is not the one that we have here with this fit, where we fit the whole data set. In order to use this, we would have to refit it with a train size and test size, as here using this train test split. Okay, so let's go further first, and let's build a model zoo that we have talked about. So I will pull in here a couple of classifiers that we have. So we have from scikit-learn basically neighbors. We can import basically the car neighbors classifier. Okay, this is a nearest neighbors classifier, without going into further details. Which ones are interesting? For instance, I have here tree. We have the decision tree. Yeah. Okay. tree classifier. Okay, we have from basically from scikit-learn we can use not only trees, we can even build forests. So for instance, this is an in ensemble methods import random forest classifier. Okay, I don't want to go into details how all these classifiers work. We talked about the support vector machine. There are of course different algorithms. These are these different algorithms without going into details. Just to give you an idea that all kinds of methods exist. You can look them up in the scikit-learn reference. You can look them up on the internet. You will find a lot of documentation on them. I don't want to go into details into all of them. You have seen one. What you should learn in here is the principle of classification. I have already shown you the cross-validation, how to basically find the best classifier for your system if you have the computation time, if your data set is small enough, and basically how to evaluate with cross-validation if your model or if your classifier is good. Yeah, that's basically what we will do here. Okay, I will take in one more classifier to make this a bit more fun. So we have the scikit-learn naive base classifier still, and we have this one here is called Gaussian naive base. Okay, so we have these, and not to forget, just to keep him in the list, from scikit-learn svm we have the support vector classifier that we have already imported, but just to have them all here in this list. Okay, of course there are way more classifiers. Look up the scikit-learn documentation if you want to extend this list. Try this out at home, try to extend the list, play with this, play with the dataset. Maybe you find better prediction scores than I have here. Okay, so fine, so good. We have all these classifiers. When we have this, we have also our model selection up here. We should have everything that we need, and we can right now basically build our system and try it out in order to find basically the best classifiers from here. I made a little spelling mistake here from scikit-learn neighbors with an H, of course. Okay, so fine, so good. Right now, what I want to do basically is I want to create myself a little list of names so that I can address them here easier. So I will call this here nearest neighbors. Okay. Then I have basically what else do we have here? We have the decision tree classifier, so let's call this decision tree. Then we have the random forest. Then we have the naive base, so we have basically Gaussian naive base. Okay, and we have the support vector machine. Okay, so this is just a list of names. We will see rather quickly why I need it, and then in the same way as I use this, I will create a list of classifiers. Okay. So how do I create a list of classifiers? Let's call them CLFS for classifiers, and let's make this list. And in this list, I basically just call the functions of all of them. So I have my nearest neighbors classifier. Okay, this is not what I want. I want to copy paste this. Let's copy from here. Let's paste in here. And basically we want to have the function here, and we can use, as this is an object-oriented programming framework, we can just use these functions here and put them into this list. It doesn't make any, it doesn't matter. These are objects like anything else, okay? We have the decision tree as the next one. I have to copy paste, of course, I'm sorry. Okay, we have the random forest. And we have this knife base classifier. And to make it a bit more interesting, we will do something more. So we will take basically here the Gaussian and me, if I arrive to copy paste, and then we had here basically, as we remember, we had our support vector machine, and of course I will call this here linear support vector machine. And just to show out that basically all these models of course have hyperparameters that you can set in here. And one hyperparameter, for instance, for the support vector machine would be, do I use this linear support vector machine or this kernel trick, as we talked about it in the lecture. And I will basically create two support vector classifiers, one with the kernel trick and one without the kernel trick. So this is first the linear one. So let's use the linear one. How do we use the linear one? As you remember, we can use here support vector classifier, and we can say kernel, and we want the linear kernel, okay? We use also the kernel track, support vector classifier, and here we use kernel. And we use basically radial basis functions, so RBF. A kernel which uses radial basis functions in order to build the space, which is of course not the Euclidean space then, but the curved space, where we still can use the support vector classifier. Okay, so in order to update this, we will also update the names up here and add basically at the end the RBF radial basis functions support vector machine. Okay, I will call this the RBF support vector machine. Okay, so let's evaluate our lists. Let's close this list first here, evaluate this, and we have then two lists with the classifiers and the names of the classifiers. And right now, what I basically can do is I have all of this set up, and as I also have, remember, our cross-validation, so I will just basically copy-paste this here, just to have you remember this. This is our cross-validation story here. Our x is basically already scaled, we have all this, we have our y, and we can then basically evaluate this in a for loop. So we have our cross-validation, and we can build something like a for loop for I in range length. And then we take basically the length of how many classifiers I have, and I can then basically here say, okay, take a classifier from my classifier list, okay, calculate me the scores using the cross-validation, okay, use the classifier, use the x, use the scaled features, use our labels. Again, I use this to numpy functionality. This might not be necessary, but just in order to be sure that we have numpy array and numpy array, we use our cross-validation that we have here. We already built this, but we just do it here a second time. And then we can print this basically like this, and we can say here, as this has the same indices as my list down here, I will just use here names, and then I can use this kind of, just to see it also, this C notation, in order to build something like this here. What's going on here for the people that don't know basically? So this is basically C notation, and you can build a string like this here and say, okay, this is basically it's a floating point number, and I want just to have it written up to 2 digits. Okay, very easy. 0.2, 2 digits in the floating point number that we have here, plus minus 2 digits also in the floating point number, and then which floating point number I define this with this percent sign here, and then it automatically takes a floating point value from behind, converts it to a string, and prints it only with 2 digits. Okay, this is all that's going on here. If you use this percent notation, this is a bit this C notation, so this comes from the C language, if you want to know. But here this is kind of string conversion. How this is one other way, instead of writing string and the floating point number. But this way basically I can convert it so that it only prints 2 digits. Okay. Okay. So what I need then, I need a tuple, as I have here 2 values. So I use my scores mean basically, so I show here the mean, and then of course plus minus scores and the standard error that I will calculate. So I take the standard deviation times 2 for the standard error that I plot here, so that I get a good estimation of how good my basically my classifiers perform. Okay. And right now I run this, and hopefully this runs right, and we get a nice list out of our different classifiers. So we see basically we have here the different classifiers right now that we have evaluated, and we see which ones performs best and which one doesn't perform so good. So we see, okay, we have the nearest neighbors 85 plus minus 3, we have the decision tree which doesn't perform so well, we have the random forest which performs a bit better, we have this Gaussian knife Bayes, but which also has kind of this 0.05 here basically. So we are at least at let's say at 0.84, which is better than the nearest neighbors, which is so far the best here. When I look at the linear support vector machine, it looks like this. The radial basis support vector machine in this case doesn't forcibly perform better. Okay, which one would we like to use in this case? Of course, this is the best model according to this solution. Okay, so we will train this model and use this model in the end. So how do you train this model right now? So this was kind of the test, which one is the best. We did this with cross-validation split, train size, test size 0.1. So right now I need a training set, test set split of 0.5 and make a final prediction if this works. So how do I do this? I use my training test set split in order to do this. So I have xtrain, xtest, ytrain, ytest. So this is basically how the train test set split functionality in scikit-learn works. So I use my xs, my y, 2 numpy as I always do it. Here we say test size, so train size 0.5, test size 0.5, and that's basically it. We can give this also a random state so that we always get the same values out here. Random state is just a seed. We can use here an integer number, so to always use the same seed and get the same train test split if you want to generate different train and test splits. Okay, this is all not so important. We just want to have train size, test size, and as we see, this gives us back to with this xtrain, xtest, ytrain, ytest variables that we can use in order to get the training and test labels. Okay, so we performed the split. Our test on our data set is right now split into training set and test set split, actually what we want. This is also what of course we did during the cross validation, but we need to basically to split this, because if we use different data set sizes, it can happen that we overfit or underfit, and then our scores might not behave as we have it here. So we said the best from our model selection here was the Gaussian knife Bayes. We did this with cross-validation. We performed model selection in this case, in order that we found that the Gaussian knife Bayes classifier performs as the best, without going into details what this classifier does. Okay, so let's build a classifier with this Gaussian knife Bayes. So let's do CLF. Let's say final is this one. Gaussian knife Bayes. I always forget to type copy. So let's copy this here. Let's paste this here. And it's this classifier that we want to have as our final classifier. And we will right now fit it on this test set. So xtest, xtrain, ytrain, so on our training set. Okay, and then we can basically score it, and basically we can score it with the test set. And we get a score of 0.86, which is of course in this range and probably what we want to have. Okay, this is our final trained classifier as we want to have it. And if we want to use this in order to build a prediction, we can use this with this predict functionality, and then can say from one of the tests that basically if he has cancer or not. So I can basically use xtest, something like this, and use here let's say the first value of the test set, and then this always basically wants to have a list. So let's give it a list, and it says that the first one of the test set doesn't have cancer according to the prediction. Yeah. If of course right now I want to have a new one predicted, just to remember, what would you need to do? If you have these values, you would have to have these values basically in a number array. So you can build a linear number array like this with the values that you have. You would need these values. You would have to pass them through the standard scaler. So if the standard scaler transformed, then you get your new one out, and then you can input this new one into this final predict function and get out what it would look like. Okay. I hope you had fun with this. Basically, there's also, in order to do this, there's also a pipeline functionality for this course. We will not go into it. This is a basic course here. I hope you get an idea on how to use model building, how to build classifiers, what they look like, how you can train different classifiers, how you can evaluate their performance in the right way using cross-validation, how you can do training and tested splits, how you can fit classifiers, how you can score them, how you can make predictions. That's basically it for this course. I hope this was instructive for you. Goodbye and see you in the next one. Bye bye.